right, good morning everyone. My name is Mike Skeen. With me is Nick Truesdale. We're going to share a little bit about the DayStar project with you. So, I think most people in this room will recognize the Hubble Space Telescope. Provides great images and science return like the Hubble Deep Field here. However, there's one big problem with space telescopes like these. That's that they're very, very expensive. So another option is to have a balloon observatory and put a telescope on a high altitude balloon. So since these balloons can float above most of the distorting atmosphere, their optics are diffraction limited, which means that the quality of the image you have is only determined by the properties of those optics. There's also improved access for improvements and repairs to these payloads. You can easily bring the balloon back down to the ground, fix it, and send it back up again. These payloads also have significant cost savings. You don't have to buy a big rocket. You can also use a lot of commercial off-the-shelf components, which means you don't have to test as much, you don't use as much flight heritage, and those components are ultimately cheaper. These balloon payloads still can provide long duration missions as well as large payload capabilities, so that's not a limiting factor either. One such example of a balloon payload is a sunrise mission. It's a sun imaging UV telescope. It's diffraction limited, and it operates during both daytime and nighttime altitude. So, just as orbital observatories need altitude determination, so do these balloon payloads. The star tracker is commonly used to do this. It takes an image of the star field, finds all the stars in the frame, and compares that to a catalog, and outputs the pointing state of the payload, usually on the scale of arcseconds. So one such star tracker designed for sounding rockets is the ST-5000, built by the University of Wisconsin. And our customer flew one of these on a balloon flight recently, and the sensor saturated 20 minutes before sunrise just due to the scattering in the atmosphere. So it's not usable in the daytime. So what's needed is to increase the accuracy of the system like the ST-5000, as well as allow it to operate in daytime conditions to support a balloon observatory. So an overview of the design problem. A normal star tracker has nothing in between the lens and the stars. So the viewing conditions are optimal, you can see the stars well, and most of your accuracy is determined by your image processing algorithms. However, on a daytime star tracker, the viewing conditions are much worse. It's sort of similar to dust on the ground. You can see on the image on the left here, right part there is the moon, but there is a star, but it's way down there, you probably can't even see it. So what the main concern then is image quality, actually seeing many stars and seeing them well. So DayStar is a senior project here. It's designed to be a diurnal star tracker, specifically for payloads on high altitude observatories. And for the scope of this project, we're just building ground-based prototype. So here's a solid model of the system. In blue is the telescope designed by Ecomox Inner Science. That focuses light onto our sensor enclosure in orange there. That collects all the light data and sends it over to our computer as an off-the-shelf processor and a custom power board, which then processes all our images. We also have a baffle of purple up the front to reduce some of that scatter light in the atmosphere. So as it's a senior project, we go through the whole design cycle, starting with our requirements, moving into performance modeling, continue on with detailed design, component selection, interface definition, and then starting this semester, we started building our hardware and iterating and improving those designs. And then just recently have been doing system testing. So DayStar is the white telescope you see there. So I'll get through a little bit some of these components in a bit more detail. We've got our optic system, which as I said, it's the white telescope there. It's responsible for focusing light as well as filtering out some of the scattered light. And that light is focused onto our CMOS sensor. We've designed the board and interface electronics for that. That collects all the light, digitizes it, and sends it to our computer. That's an off-the-shelf computer. However, all the software on it is, most of the software on it is custom written. That processes all of our images and turns starlight and pixel data into attitude data. All this is supported by a custom power board that we built. That power board is also capable of measuring diagnostic data and watching over the system to ensure it runs smoothly. Finally, we have our interfaces to the rest of the balloon payload structure.
All right, so as Mike said, the biggest problem we need to solve when designing a daytime star tracker is seeing stars in the daytime environment in the stratosphere. And even at 35 kilometers during daytime up there, it's similar to dusk on the ground if you go outside at about 8 p.m. tonight. You can imagine you won't see very many stars. So we need to be able to see those stars, and the solution is to make use of the fact that the sky and the scattering in the sky is very blue. This plot at right shows a curve of the background light, which is in blue, and the black line shows the light that we might see from a typical star. And DayStar is designed to make use of the fact that while the sky is very bright, it's blue, and we can filter that out. In that way, we can see stars that are either peaking in the visible spectrum or even out in the red end of the spectrum. We do this by implementing a long pass filter in our telescope, which is at 620 nanometers, so there in the middle of the image. We also use a camera with very good red performance so that we can see those red stars. Now qualitatively, this is a fairly straightforward solution. We just put a filter in place and use a good camera. But in order to quantify this and determine the accuracy of our system, we had to design a fairly in-depth model. This model has to parameterize both the background light that we see as well as the light we see from a star in terms of wavelength, because that's the driving parameter of our system. Once we do this, we can determine the signal-noise ratio of any given star in our image. And we combine this calculation with the star population model. What that essentially is just the typical field of view that we would see and the characteristics of the stars we see in it. And from that, we can determine the total number of stars that we see that have a sufficient signal-noise ratio to be analyzed by our software. Really briefly, the most time we spent modeling was on our corrected star model, which we designed from the ground up. And what it does is it goes in and corrects for the fact that even for a common visual magnitude, stars that are either red or blue are actually putting out quite a bit more light. They're just in other ends of the spectrum that aren't taken into account. So this image shows a magnitude 8 star, a visual magnitude 8 star, but you can see that as you move off into the red, stars actually start putting out quite a bit of light. And we'll be leveraging that fact in order to see even dimmer magnitude 7 or 8 stars, hopefully during the daytime. Nothing else. So now the final step is to take our image quality analysis and combine that with our algorithms analysis in order to determine the performance of our system as a whole. Our algorithms team wrote software that both detects stars in an image and analyzes the centroids of those stars and where they're located in the image. And based on the accuracy of each individual centroid, we can combine all of those and get an attitude solution and determine the accuracy of that solution. And so assuming a 0.9 arc-second accuracy for our individual centroids. That is the green curve on the plot. You can see that in order to satisfy our 0.1 arc-second accuracy requirement, we need about 15 stars. So combining that with the other portion of our modeling, which was image quality, we determined the number of stars we see. And during nighttime, that's about 45. During the daytime, we expect to see really just the brightest and the reddest of stars. And we expect to see five stars during the day. And as I said, at nighttime our requirement is 0.1 arc seconds, and we far exceed that. And the daytime is relaxed a little bit since it's just a proof of concept. So we still meet our 1 arc second requirement. We actually get pretty close to our 0.1 arc second requirement for nighttime. So it's pretty good. So as Mike said, last semester we were modeling and we were running our project, but this semester we've been working on designing and building all of our subsystems, integrating those and testing them. So we began on each of the individual subsystems. Here's Zach designing or building our camera board. We then began integrating these subsystems together, testing their functionality, how well they communicate, and then finally wrapped up the entire subsystem, or the entire system rather, did benchtop testing, and then moved that out to Summers Washington Observatory and began taking images of the sky. The biggest thing that we found during our testing was that we have a couple fairly severe optical aberrations that make it pretty difficult to see stars, especially during our daytime conditions. What this means is that because stars, we have two issues. One is called vignetting. It means that the edges of the image are very dim compared to the center. And the other is called a coma, which takes light from a star. You can see in this image, it's supposed to be focused down to a few pixels, and instead it gets blown out in a fairly irregular shape. So this decreases the accuracy of our centroids and therefore the number of stars detected. So the ramification of this, during daytime, we were able to see some very bright stars, but only in certain regions of our image, and we therefore were not able to obtain a attitude solution, though we did see that the camera does not saturate, and so we're hopeful that with further testing we'll be able to get a solution. During the nighttime, while the centroids are fairly distorted, we were still able to see plenty of images. They're not quite as accurate as our modeling, however, we can still generate a relative attitude solution. I'll show that in the next couple slides. Here's an image, or a series of images we took at Summers Bosch. It's 2,500 images stacked on top of one another over a duration of 30 seconds. And you can see the stars are all streaking in a fairly uniform motion. Near the edges of the field, you can see centroids are a little less accurate. They're spread out, and again, that's based on the coma and on the vignetting. It's harder to see things in the edge of the view, edge of the field. However, in the center, we've got very nice uniform centroids. If you zoom in on those, you can track them. If you fit a line to this is the motion of the sky as the Earth moves. This is, again, a 30-second duration. That's the rotation rate of the Earth. So you can subtract that out and then tie all of things together and determine the RMS error between them. And that's the process that we're in the midst of working on right now. We'll talk about further during the closer session. But that is the process we're taking to verify our accuracy requirements. So, in conclusion, high-altitude balloon observatories are a great way to do observational science over orbital observatories. DayStar is a ground-based prototype that shows that even during the daytime, we can avoid saturating and hopefully show that we can get an attitude solution. And then this is a summary of our estimated performance. Again, we're working on getting our actual performance the next few days to wrap up the semester. With that, we'd like to acknowledge all the support we've gotten, especially our customer, Elliott Young from Southwest Research, and Dr. Scott Palo, who has been our advisor for this semester, as well as the rest of the PAB and staff that have helped us over the semester. Are there any questions?
What fraction of the atmosphere is above the balloon launch?
I don't have an exact number, but it's over 99%, or sorry, we're above 99% of the Earth's atmosphere. So not very much at all.
I didn't understand what was limiting the optics. What, is it the atmosphere that's limiting, or is it the optics in the telescope itself?
I mean,
Well, you said you had two optics problems, especially the second one where you're sort of getting it.
yeah, that's in the optics itself. It's an issue with some of the lenses, and something that we've identified. One of the lenses that condenses light on the sensor has issues focusing the light uniformly. So we have picked out another set of lenses that we're hoping to integrate those over the summer as we move forward in getting this ready for a balloon launch.
Any other question? If not, thank you very much.